Okay.
Well, so our next speaker is Catherine Kallin. I mean, Catherine was a graduate student here at Harvard along with me when a few years after Bert started at Harvard, and so it's a pleasure to welcome her back, and she'll tell us about chiral superconductivity.
Okay. Thank you very much, Sabir. I have a rare medical issue. I have to sit down giving this talk. I mean, it's nothing serious, but I can't stand up too long without getting dizzy. So yeah, I'm going to talk about multiband chiral superconductivity, but first it's a great pleasure, and I'm really happy to be here to celebrate Bert's 75th birthday, and so happy birthday, Bert. As Sabir said, I was a graduate student of Bert Halperin's back in the 1980s, and here's a picture of Bert and me with a couple other students in Santa Barbara where Bert was on a sabbatical. So I've learned a tremendous amount from Bert. It continues to influence my physics and career. And in particular, one of the problems we worked on was cyclotron resonance from filled Landau levels, and that taught me about Cohen's theorem and the frequency-dependent conductivity, which later helped me understand the Kerr effect in chiral superconductors, and I'll mention that towards the end of this talk. So chiral superconductors are a rather novel type of superconducting order. The Cooper pairs have an angular momentum, so this is a state that breaks time reversal symmetry. It has topological order, analogous to some of the quantum Hall states. It's also characterized by a Chern number, like some of the quantum Hall states. And because of the topological order, it has special chiral edge modes. The best studied examples also have evidence of triplet superconductivity, such that they can, in principle, support half quantum vortices, and one has the possibility of Majorana modes in the vortex cores. There's a number of systems now that are candidates for bulk chiral superconductivity. Here I'm just going to focus on the best studied example, strontium ruthenate, and towards the end I'll say a little bit about UPT3. So strontium ruthenate has the same crystal structure as some of the cuprates, but it has 3 bands crossing the Fermi energy. So there's 3 sheets of the Fermi surface shown here called alpha, beta, and gamma. Like the cuprates, it's a highly anisotropic, quasi-two-dimensional material, so there's very little dispersion along the c-axis, and one often uses two-dimensional models to describe this. So here I've shown the Fermi surfaces in the AB plane, and the 3 Fermi sheets come from d orbitals on the ruthenium atoms, where the gamma sheet, which is this nearly perfect circle here, comes from the dxy orbital, so it's a two-dimensional band, whereas the alpha and beta come from dxz and dyz orbitals, so they form quasi-1D bands, which then hybridize near this 1-1 direction. And over 20 years ago, Miano discovered superconductivity in this material, in the very best samples it superconducts below 1.5 Kelvin. And so since then, there's been many beautiful experiments on strontium ruthenate. And in particular, there's many experiments that point towards odd parity or triplet superconductivity and broken time reversal symmetry. And if you put these together with the crystal symmetry and some energetics, that picks out a particular chiral p-wave order parameter where the Cooper pairs form a triplet with 0 spin projection along the c-axis. This is picked out by spin-orbit coupling. And the orbital part has the symmetry of sine kx plus or minus I sine ky. The I there says that you break time reversal symmetry. The plus and minus are 2 chiralities. They're degenerate, so in a macroscopic sample you might have coexisting domains of these 2 chiralities. And in the and I should say this plus or minus I means that you have a winding of plus or minus 2 pi as you go around the Fermi surface in the AB plane. So that's the topology. And in the shortly after the discovery of superconductivity in this material, it was proposed that the superconductivity may be driven by ferromagnetic fluctuations on the gamma band with only much weaker induced superconductivity on the alpha and beta bands. And this makes sense because the gamma band comes very close to these M points, which are Van Hove singularities that give you an enhanced density of states. And there was some experimental work that was in sort of confirmed this picture, and there was subsequent theoretical work. And this theory, this so-called one-band theory of strontium ruthenate, was successful in explaining a number of experiments. However, there were some problems with it and discrepancies. One was the absence of the observable edge currents that I'll say more about on the next slide. The presence of low-lying excitations, the specific heat and thermal conductivity, as well as other measurements, see low-lying excitations suggestive of nodes in the gap. And this simple theory predicted a gap all around the Fermi surface. I should say this simple one-band theory also predicted that the sign kx, this nearest neighbor pairing, would dominate. Also, this theory had difficulties explaining the Kerr effect that was observed, which is connected to a Hall conductivity. And more recently, there were experiments of C-axis tunneling by Seamus Davis that gave evidence of strong superconductivity on the alpha and beta bands. So let me turn to this issue of the absence of observable edge currents. So because the chiral p-wave state is topological, there must necessarily be chiral edge states that disperse through the band. And these edge states give rise to a spontaneous equilibrium current that flows around the edge of your sample. If you have a single domain, if you have multiple domains, it flows around each domain. With the direction set by the chirality. Of course, the field has to be zero inside the superconductor, so there's equal and opposite screening currents. But because of the two different length scales involved, there's still a residual field at the edge of the sample or the edge of the domains. And this is not such a small field. It was for strontium ruthenate. It was in the early models was predicted to be 10 to 20 Gauss. And in fact, mu-SR measurements on strontium ruthenate are interpreted as seeing internal fields due to internal domain walls. However, if you take your sample and you scan a squid pickup loop over the top surface of your sample, you'd expect to see fields from these edge currents, either at the edge as well as at any domain walls that might come near this top surface. And exactly that type of experiment was done 10 years ago by John Kirtley and Catherine Moeller and others at Stanford, and they saw nothing. It was a null result, and subsequently there's been intense searches for these edge currents, using smaller samples and higher sensitivity, and they've all been null results. So experiments put an upper bound on these edge currents, which is about 3 orders of magnitude smaller than the simple chiral p-wave prediction. So that's a problem for the theory, 3 orders of magnitude. And the simple prediction comes basically from this one-band model that's predicting a sine kx plus I sine ky pairing, which gives an edge mode that disperses roughly linearly across this gap. So this is the energy as a function of the momentum along the edge that you're looking at. And the current from in this situation it's not topological, but it's highly constrained. The current can be reduced from, example, disorder at the edges, but it tends to be order 1 corrections or reductions in the current. And the largest reduction found was if you assume that the order is so strong at the edge that you have a metallic region at the edge, that can reduce the current by close to an order of magnitude, but still not the 3 orders of magnitude needed to reconcile with experiment. More recently, we've found that the key to getting really substantially reduced currents in chiral P wave is to have edge modes that don't look like this, but that have extra zero crossings. And there's different ways of getting such dispersion of the edge mode, but the one that's relevant to strontium ruthenate is to have highly anisotropic pairing. That is not nearest neighbor, but perhaps mixing in second neighbor, sine kx, cos ky type pairing, or further neighbor, sine 2 kx, sine 3 kx, etc. And it's not that the current is necessarily small when you have these extra zero crossings, but these zero crossings allow for spectral flow and consequently sensitivity to the microscopic details. So the current could be small. And here I'm just showing a calculation of a 3-band model with the band structure of strontium ruthenate for a couple different parameters where one is varying the anisotropy of the pairing, so mixing in this case, more and more second neighbor pairing. And the current, just showing that the current changes. It can be large and positive, large and negative, but it can also be zero. So you at least have the possibility of a reduced edge current in an anisotropic model. So in strontium ruthenate, what could cause such anisotropy? Well, it's really moving away from the 1-band model and including the physics of all 3 bands. And these calculations were first done by Thomas Scafidi and Steve Simon's group. He did what are called weak coupling renormalization group calculations. Basically, he started with a realistic model of the band structure of strontium ruthenate, included all the on-site interactions, that's the Coulomb repulsion and Hund's coupling. The approximation is assuming that these interactions is small, so you can do a perturbative analysis and you look for the leading instability to superconductivity. This calculation, you find that you can get either D wave or P wave, depending on the interaction parameters, but there's a range of interaction parameters that stabilizes chiral P wave superconductivity. And here I'm showing the gap functions on the 3 bands for a parameter that's just chosen to fit the specific heat and tunneling data. And so this is for the alpha, beta, and gamma band as a function of angle as you go around the Fermi surface in 1 quadrant. So the fact that this has such angular dependence, tells you you've got anisotropic chiral P wave pairing. In this case, you're mixing in second neighbor as well as sine 3 kx type pairing. So what's interesting is if you just take these results, which, remember, the parameters are set to fit specific heat and tunneling data, and you calculate the current, you find that the current is substantially reduced. So here's this showing the total current as a function of temperature. The upper curve here is just the simple sine kx type model with an ideal edge. The bottom one here is the results of this weak coupling calculation with a strongly disordered metallic edge. And you see there's a range of low temperatures here where you get 3 orders of magnitude suppression. So it's interesting that the weak coupling calculations with no additional parameters just happens to give you a very small current, and that could be an explanation of the lack of observable edge currents. A more robust way to get a small current in a chiral superconductor is to not have chiral P wave pairing, but to have chiral D or F wave pairing. I mean, naively, you might think this would give you a larger current because each Cooper pair has a larger angular momentum. But there's a symmetry here where you can show in the continuum limit the current exactly vanishes. And it's basically because the current is related to a current. You've got two powers of velocity or the current vector, which is picking out like an angular momentum 1. And when you pair that with higher angular momentum, the whole thing averages to 0. This is probably not relevant to strontium ruthenate because there's no reason to believe you have chiral D or F, but it could be relevant to UBT3 and other chiral superconductors. So these weak coupling calculations, as I argued, they give a substantially reduced current. They also give low-lying excitations because, see, these near nodes, particularly on the beta band, describe low-lying excitations. It's interesting that the weak coupling over a wide range of parameters has comparable superconductivity on all three bands, and there's some experiments pointing to that, the specific heat and the tunneling measurements. But although they have comparable superconductivity on all three bands, it's not because the bands are strongly coupled. It's that each individual set of bands, the gamma band and the alpha and beta bands, on their own would like to superconduct, interestingly, for somewhat different reasons. The gamma band is driven by intra-band interactions, whereas the alpha and beta, the superconductivity is driven by Cooper pair scattering between the bands, here picking out a Q vector, which is largely responsible for a lot of the anisotropy in the gap function. So the message from strontium ruthenate is that it seems like the microscopics of strontium ruthenate really matters in trying to reconcile theory and experiment. So in the last few minutes, I want to say a little bit about UPT3, which is another proposed chiral superconductor, because this is a problem when I guess I had a chance to briefly discuss it with Bert when he was visiting Stanford a couple months ago, and we overlapped there. It's something that it's currently still in progress. I'm working on it, but UPT3 is a heavy fermion. But below about 5 Kelvin, it forms a nice heavily renormalized Fermi liquid with a decreasing resistivity with lowering temperature, and its Fermi surfaces are fairly well characterized. There's 5 sheets of the Fermi surface. It has an HCP, distorted HCP structure, so that's hexagonal layers stacked AB, AB. Has an interesting phase diagram. If you just focus on 0 applied magnetic field, there's 2 superconducting transitions, and it's thought at the upper transition that you go into an F wave superconductor. With this symmetry, it's like a D wave in the plane, if you like, and a power of Kz. And that below the second transition, a second F wave component is picked up with a relative phase of I, such that you have a chiral superconductor. And one experiment that lends evidence for this particular type of pairing is beautiful experiments by Dale Van Harlingen and others, where this black thing is the UPT3 sample, and they built these Josephson junctions all around the sample to be able to measure the critical current as a function of angle in the AB plane. And what they saw was when they went below the first transition, they saw a 4-fold anisotropy, which is quite striking for a system with a hexagonal crystal structure. As they then went to lower temperature below the second transition, the anisotropy washed out, and that's exactly what you expect for this order parameter as you pick up the second component. More recently, Aaron Kapitulnik and his group have measured a Kerr effect in UPT3. So what's measured there is the Kerr angle. It's a rather complicated optical response, but it's directly related to the Hall conductivity. And in this case, you're not there's no applied magnetic field, so it's an anomalous Hall conductivity, which can only happen if you break time reversal symmetry. And this is the data just showing that as they go below the first transition, as signaled by this change in the susceptibility, the blue data, that there's no Kerr angle until they go below the second transition, as you'd expect for that order parameter. So there's also been, the Kerr effect has also been observed in strontium ruthenate. I didn't show that data. In fact, it was measured in 2006, and shortly after the data came out, there's several papers and preprints that got agreement with the data. But if you look at them, they were basically doing a one-band model in the continuum limit. They had Galilean invariance. I knew right away that couldn't be right because of what Bert taught me. Because of Cohn's theorem, you have to break the translational symmetry. The uniform field just couples to the center of mass degrees of freedom, and you wouldn't be sampling. It's not enough to just spontaneously break time reversal symmetry. So you can break the translational symmetry by disorder, and that's one possible explanation. Strontium ruthenate are clean samples, so that's a little bit unlikely. UPT3 are ultra pure samples. It's a very unlikely explanation. My postdoc Ed Taylor and I identified an intrinsic source for the Kerr effect in a chiral superconductor. It requires a multi-band chiral superconductor, and it also invokes interband pairing. It's a possible explanation in strontium ruthenate, and it, in principle, might explain UPT3. However, one can show that the Kerr angle is actually 0 for chiral D or F wave in the continuum limit. This again follows from symmetry similar to the current, which would suggest that you're going to get a rather small Kerr effect in UPT3. And I should have mentioned that the Kerr effect observed here is more than 10 times larger than that in strontium ruthenate. So, but very recently, just over the last part of 2016, there's been a number of papers pointing out that because of the symmetry of UPT3 that has a non-symmorphic space group, that one can have a more complex order parameter. In particular, this work by Yanasi points out that you can mix in a D wave component to the F wave. Now, usually this wouldn't be allowed because D wave is even, F is odd. It's like you're mixing singlets or triplets or pseudospin singlets, pseudospin triplets. But you can mix in a D wave component that's odd in the interlayer spacing, this AB layer index, such that the whole thing is odd, and you can show that it transforms under the same representation of E2U as the F wave. And this changes the symmetry completely. For example, you can show that you do have a Kerr effect in the continuum limit. Our preliminary calculations show that this should support a larger Kerr effect. It also gives rise to particular low-lying excitations, and in contradiction to Blount's, you sort of escape Blount's theorem because of this symmetry, at least on some regions of the Brillouin zone, and you can have line nodes and low-lying excitations that are observed in UPT3. So this is work that's just sort of coming out now. So all the previous analysis of UPT3 has more or less been in the continuum limit, and it's only now that people are turning to the microscopics and looking at this in more detail. So in conclusion, I'll just say that we learned from strontium ruthenate that the microscopics can matter even by orders of magnitude. So in UPT3, we're learning that there can be significant effects there of the microscopics, and hopefully there'll be more theory and experiment on UPT3 that illustrates some of this. Thank you.
Thank you very much, Catherine. Okay, here.
I have an elementary question. The main evidence for breaking of time reversal is the Kerr effect?
For strontium ruthenate, there's the Kerr effect. There's muon spin resonance that sees additional internal fields turn on with TC. There's tunneling data where the clearest one was a corner junction. Unfortunately, they only saw it in one corner junction. But there's tunneling data on an AC face that sort of requires some complicated analysis, but with domain walls, it brings in the time reversal symmetry. So there's multiple experiments pointing to
The kind of simplest evidence is the Kerr effect?
Well, it's, mu-SR in principle is pretty simple because they're just seeing an extra relaxation of the muon spins that turns on below TC. It's just that it doesn't give you spatial, like you don't know exactly, anyway, and there haven't been detailed comparisons with the MuSR, but I'd say those are the two main ones. I mean, you'd obviously like a corner junction for chiral P wave to check that PX, PY has an I there. Unfortunately, it seems, it's possible domains are interfering with that. They've only seen it in one junction.
You mentioned this STM data of Seamus with stronger superconductivity in other bands. Is that compatible with the model you presented?
Yes, because if you're tunneling into the C-axis, you don't expect to be very they only see one gap. And so if it's only going to be one gap, it's got to be the alpha and beta bands because, the DXY orbitals, they have essentially almost no dispersion along the C-axis. And so they're seeing one gap, which, is already, 4 KTC or so. It's a large gap.
That's part of your model also for the reduced currents, the edges.
Yes, yeah. In fact, that's where they fit the parameters, because we don't know what the interactions are, the Hund's coupling relative to the repulsion, but those are fit to nicely model the specific heat and the tunneling data, because there's also tunneling in the AB, into the AB plane that would show you the other gap. Yeah.
More questions?
What are the size of the domains that one expects?
Yeah, well, so domain costs you energy. So if you had an ideal sample that you could cool as slowly as possible, you wouldn't get any domains, presumably. That is a sticking point on strontium ruthenate that, all the signatures of time reversal symmetry tend to invoke domains in their interpretation, but they have different length scales. They vary from of order, 1 micron to, about 100 microns. It could be differences in sample prep and that. It's not well understood. But you certainly, you don't, once, if you had your domains getting as small as the penetration depth or something, you're severely interfering with the superconductivity because there'd be these currents all over the place and a suppressed order parameter. So you expect them to be big.
Hi. So my question is regarding this anisotropy. As long as you keep it odd wave, can you get mixing of L equals 1, L equals 3, like all together?
So yeah, of course on a lattice, that isn't that well defined. So maybe what's well defined for the state is the churn number. So for a simple, right, because on a lattice, when you're mixing in higher harmonics, yes, you can analyze it in terms of mixing in different angular momenta, but the churn number is topological, and so yes, on a square lattice, the churn number can change by plus or minus 4, and in fact, I didn't mention that, but these particular results that we're fitting to have on the gamma band, they have a churn number of -3, so. Which means the current's going to go in the opposite direction from that band compared to what you expect, et cetera. So yeah, as you crank up the anisotropy, you say you started with churn number 1, that's a winding of 2 pi as you go around the Fermi surface. As you keep increasing it, you'll go through a transition to churn number -3. But you can get small currents with either churn number 1 or churn number -3. It sort of depends where you are on the anisotropy scale.
Okay.
Thank you very much, Catherine.